Okay, hey guys, so you should have this Math 2 review topics packet out in front of you, and I'm going to work through part of this worksheet with you right now, all as a class, and then afterwards you guys are going to finish the spots that are not done as a team at your table. So please don't work ahead as I'm working on these because I want you working as a group after we go through these examples together. So this is the purpose of these problems in this packet is to review a lot of the Math 2 stuff that you've probably forgotten about or just need to review from Math 2 that you guys are starting to see pop up in the homework. So it is worth stopping and reviewing these just to get that solidified in your brain. First, we're starting with right triangle trig. So I'm going to go a little bit quickly because these are all review topics, but if as a class you guys feel like you need to pause and rewind, that's totally fine. Also, this will be linked on Schoology, so you could always go back and check it out later if you need to do that. All right, so for the right triangle trig, we see a right triangle here. This side opposite of a right triangle is the hypotenuse, and then whichever angle you're referring to, so see this theta right here, so theta is in this corner, then the opposite side would be right here, and the adjacent side, which just means next to, is right there. So when we're talking about sine, cosine, and tangent, those are all functions of an angle value. So that will require you to remember, hopefully you learned SOHCAHTOA to help you remember what the ratios are for each of those three trig functions. So SOHCAHTOA, the S, the C, and the T are sine, cosine, and tangent, and the next two letters are the ratio that you're setting up for those functions. So the sine of theta is, you look at SO, and it's opposite divided by hypotenuse. So sine is the opposite side of the angle. The sine of theta is opposite of theta divided by the hypotenuse of theta. And remember, the hypotenuse is always opposite of the right angle. Cosine, so AH, so it's the adjacent side, so right next to theta. Oops, that's an I. Divided by the hypotenuse. And then we have tangent, which is the opposite divided by adjacent. Okay, so those are our three main trig functions. There's other trig functions, but those are the ones we're focusing on. Okay, so let's do a couple of examples. I'm actually not going to go straight to example 1. I'm going to jump down to example 2 for a second. And let me zoom out. Okay, so use trig ratios to solve for the variable in each figure. Write each answer to the nearest 10. So I'm looking at this right triangle. I have my hypotenuse opposite of the right angle. 15 degrees is the one angle that we do know. We want to know the value of y. So to set this up, you just need to think about what two sides you have. We are working with the opposite side, and this side next to 15 degrees is the adjacent side, not the hypotenuse. So I have opposite and adjacent. So then you go back up to your SOHCAHTOA and look at which one of those three functions, sine, cosine, or tangent, deals with opposite and adjacent. So it would be O and A. So that is O and A with tangent. So I'm going to use the tangent function here. So I know the tangent of 15 degrees is the ratio of the opposite side, y, divided by the adjacent side, 38. So to solve for y here, all you have to do is undo what's happening to y, which is division by 38. So we'll multiply by 38. Cancels on that side, times 38 on this side. So the y is going to end up equaling 38 times the tangent of 15 degrees. So this is where you'll grab your calculator, and we just want to type that in. Before you do, it's important that your calculator is in degree mode. There are two different modes for angles, radian and degree. So if you see right here where my cursor is blinking on radian, see how on mine degree is highlighted already. So I'm already in degree mode. If you're ever using one of my calculators, it's important that you always check that mode because it often gets put into radians for my pre-calc class. So I can just type this in directly, 38 tangent. So here's my tangent key right here of 15 degrees. Oops. Okay, let me try that again. So it's 10.18, or if we're rounding to the nearest tenth, so it would be 10.2. 10.2 units. We don't have units labeled, so I'm just going to leave it 10.2. So let's do one more, and then we'll go back up to example 1. So right here, I've got my angle. This is my reference angle, 49. The two sides that are marked are the adjacent side, that would be the x, and 23, which is the hypotenuse. So adjacent and hypotenuse. Again, I'm going back up to SOHCAHTOA and looking at which one of these trig functions, sine, cosine, or tangent, deals with those two, adjacent and hypotenuse. So I see with cosine the a and the h. So this is going to be a cosine equation. So the cosine of my angle 49, cosine of 49 degrees equals adjacent, so x, divided by hypotenuse, which is 23. Again, if I want to solve for x here, all I need to do is multiply by 23 to get that 23 off of the right-hand side and over to the left-hand side. And now all I have to do to solve for x is just compute 23 times the cosine of 49. So you can type it in, get your value, about 15.1 units. I'm a stickler for units, so make sure you guys are always careful about checking, and if units aren't labeled, you can just write units. Okay, now I'm going to go back up to example 1 because we're still using trig ratios and trig functions, but we're going to use them a little bit differently. So this problem says use the sine, cosine, or tangent. That little -1 right there, that's the inverse sine, inverse cosine, or inverse tangent buttons. And the difference between these problems and an example 2 is that my angle is labeled theta instead of an actual numerical value for the degrees. So in this case, we start in the same way. I look at my reference angle here and then which two sides I'm working with. So I'm working with opposite of the angle and the hypotenuse. I'm going back up to SOHCAHTOA, opposite and hypotenuse. So that's going to be using the sine function. So the sine of theta. I don't know the angle this time. See, last time I had like tangent of 15. This time it's just theta, and I want to solve for theta. But I know the sine of theta is opposite over hypotenuse, so 13 over 19. But I don't want to know the sine of theta. I want to know the value of theta itself. So I need to undo the sine function, which would be the inverse sine function. So technically what I'm doing is applying the inverse sine function to both sides. And that's going to undo this. So if I apply the inverse sine function of the sine of theta, the sine inverse of sine, that's going to undo it. And I'm just going to be left with theta. But I have to do inverse sine of this side too, 13 over 19. So theta is the inverse sine of 13 over 19. And on the calculator, you see the sine button right here. Inverse sine is just second sine. So I'll just type in second sine and then type in my fraction 13 over 19. So this is going to tell me what the angle is if the sine ratio is 13 over 19. So 43.17. Again, make sure you're in degree modes, and 43.1 or about 0.2 degrees. Oh, it says 100th. My bad, 100th. Okay. So that is 43.17 degrees. Okay. Part B, this one's a little tricky. People usually look at this and think it's the hypotenuse, but the right angle is up here. So across from it is the hypotenuse. So here's my angle theta, here's my hypotenuse. So we're dealing with opposite and adjacent. So that's going to be opposite and adjacent. So that's tangent. So I'm going to use the tangent function on this. I know that the tangent of theta is, so opposite 24 divided by adjacent 8. So the tangent of theta is 24/8, but I want to know what theta is. So I need to do inverse tangent of 24 over 8. And that again is just second tangent on your calculator. So you hit the second tangent keys, and then you'll see the inverse tangent right there and type in 24/8. And we'll get our value about 71.57 degrees. So there's a quick little review on right triangle trig. This is what you guys are going to come back and do as a table. So for now, again, skip over it. We're going to move on to the next review topic on the next sheet. Again, this problem as well at your table. And now we're going to move on to simplifying radical expressions. So the square root symbol and simplifying those. Okay, so taking the square root of a number that's not a square root. So 40 is not a perfect square. However, we can break that down to the square root of 4 times 10. Our goal is to break down these numbers, if they're not perfect squares, to products of something that is a perfect square. So let's just rewind 1 second and review. Our perfect squares are 0, 1, 4. So all those numbers that we don't mind taking the square root of mentally. 9, 16, 25, 36. So these are all perfect squares. We could go on and on and on. 40 is not a perfect square, but I could break it down to 4 times 10 because 4 is a perfect square. So once I've done that, now I can take the square root of 4, and that once you take the square root, it comes to the outside. So now it's 2 on the outside because I took the square root of 4 times the square root of 10. And then I would stop and think, okay, can I break 10 down into the product of something again? I can, it's 5 times 2, but 5 and 2 are not perfect squares. So this is as simplified as that rational expression can get. So let's look at the next one, 72. 72 is not a perfect square. And if you're not sure, you could always just double check and type in square root of 72. It's this decimal. It's not a perfect square, but we could break it down into 2, the product of 2 things. So then you're just going to check, okay, is 72 divisible by, and then pick a perfect square. So we'll do 4. It is, it's 4 times 18. You can keep going and see if it's divisible by some of these other perfect squares. But if you get to that point and you're like, okay, it's 4 times 18. Now I can take the square root of 4, that's 2, and then I'm left with the square root of 18. But you're not done yet, because while 18 is not a perfect square, you can still break it down into 2 numbers that multiply, where one of them is a perfect square. So really we can think of 18, if we look at our perfect squares, since 18 is also considered 9 times 2, think of it like that. Now I can take the square root of 9. So what happens when I take the square root of 9, which is 3? That 3, the square root comes out front and it gets multiplied by the 2. So bring that out. So really what we have left is 3 times 2 times the square root of 2. Oops, which is 6 times the square root of 2. Then we have the square root of -1. This, now we've talked about this a little bit in class so far. We are working with the real numbers, but we can still simplify non-real values. So the square root of -1 is I. That's it. So keeping that in mind, we're going to do the next couple ones that have the square root of a negative. So we will simplify these. Even if there's a negative, we can just pull the square root of the -1, which is I. So in this case, we've got the square root of -36. Well, 36 is a perfect square. Its square root is 6. And we can take the square root of -1, or you can think of it like this. The square root of -1 times 36. And then take the square root of each. The square root of -1 is I. And the square root of 36 is 6. So it would be I times 6. And we would just write that as 6I. And then this next one, the square root of -75. So let's break it down into its parts. That's -1. 75 is not a perfect square. However, it is able to be broken down into a product where one of those numbers is a perfect square. So think about 75 and what might be a divisor of that, or a number that can be multiplied to it. So that would be 25. Since 75 is 25 times 3, you can think of it like that. And then take the square root of -1, which is I. The square, I'm crossing that out to show like I've taken the square root of 25, which is 5. So that's going to just be multiplied by the I. And then 3 is not a perfect square, so that's still under the square root. So this would simplify to 5 times I times the square root of 3. And then these last two examples are combining square root expressions. So square roots you can think of as like variables almost, or like terms. So if I have 2 square root of 3 and I take away 5 square root of 3, so think of square root of 3 as like x. If I had 2x and I take away 5x, how many would I have left? Same thing. If I have 2 root 3s and I take away 5 root 3s, then I would have -3 root 3s remaining. So if it's the same square root, you can treat it just like you would any other term with a variable. So that's, you can combine them. So looking at number 7, I see square root of 20, -3 root 20 plus 7 root 5. I cannot combine root 20 and root 5 because they're not the same root. However, I can break down the square root of 20, and maybe that will help me simplify this. So I've got -3, and I'm going to break this down. The 20 I can think of as 4 times something, so it'd be 4 times 5, and then plus 7 root 5. So now I can take the square root of 4. When I take the square root of 4, it's going to come out here with this -3, so it's going to be multiplied by it. So since the square root, I'll just write it out. The square root of 4 is 2. So it'd be -3 times 2, and then I have root 5 still in there, plus 7 root 5. So we really have -6 root 5 plus 7 root 5. And then since I have the same root now, I've got root 5, -6 of them, and adding 7 root 5. So just add -6 of them, add 7, and you're left with +1 root 5, or just square root of 5. So there's a quick review on simplifying radical expressions. These down here, you're going to complete as a group after this video. Do not jump to it right now because we're going to move on to the next review topic. Exponential growth and decay. So you also saw this in math 2. Actually, you were introduced to this in math 1. So exponential relationships are usually modeled by this basic equation, a times b to the x. A, that number out front, is always the starting value. So the initial value of whatever you're working with, starting value. And b, the one that has x as the exponent, that's your multiplier. That's the number that you're repeatedly multiplying by over and over. Multiplier. Okay, so let's do some examples. These are almost always word problems, so it's important to remember this initial setup or the form of the equation to pick out what is your a value, what is your b value, and then you can plug them into that general form. So Jimmy's baseball card collection is currently worth, that's important, $1,400, and is expected to increase in value by 4%. So it's increasing by 4% every year. How much will the card collection be worth in 10 years? So let's think about this in terms of y equals ab to the x. A is the initial value. So currently worth is that should trigger that initial value mindset. So that is $1,400. So if we're writing this, $1,400 is my a value. So that's my a value. And then I just need to figure out what my multiplier is. So that b value. So it says it's increasing by 4%. However, the b value is not 4. If something's increasing by 4%, then if it's increasing, so instead of 100%, it's 4% more. So you can actually think of it as 104% of the original value, but then I need to write that as a decimal. So 104% as a decimal, you just move it over here. So B is actually 1.04. It's not 4 and it's not 0.04, it's 1.04. So what you're always going to do is convert this percentage to a decimal, 0.04, and then you're adding it to 1 because it's increasing. If the value is decreasing, we would subtract it from 1. So 1.04 to the x. So this is our equation. X is going to be the amount of time that passes. We want to know how much it's worth in 10 years. So you're just plugging in 10. So 1,400 times 1.04 to the 10th. And then you're just going to evaluate that with your calculator. So 1,400 is increasing by 4% for 10 years. It'll be worth a little over $2,000 after 10 years. So that is, don't forget units since this is a word problem, got $2,072.34. Okay, let's do another one. Liv bought a car for $5,000. The car's value is expected to depreciate. So depreciate, hopefully that rings a bell because it sounds kind of like appreciate. So appreciation means the value is going up. Depreciation means the value is going down. So I'll just put a little down. It's going to depreciate by 12% a year. How much will it be worth in 7 years? Okay, $5,000 is what she bought it for. That's the initial value. So $5,000 is our A value. The multiplier, again, so it's depreciating by 12%. 12 is not our B value. First, we convert it to a decimal, 0.12. But 0.12 is also not our B value. Remember, if we think about 100% of the value, that would be $5,000. If it's depreciating by 12% or 0.12, then we subtract 0.12 from 1. Or you can think of it as taking, if you have 100% and you take away 12%, then you're left with 88%. And then you just need to write that as a decimal, which would be 0.88. So our B value is 0.88. And this is where I see a lot of mistakes because 0.88 is nowhere in this problem. You have to reason your way to it. If it's depreciating by 12%, 0.12, subtract it from 1, and it's 0.88. So if we want to know in 7 years, we would just calculate it like that, 5,000 times 0.88 to the 7th. So in 7 years, it'd be worth about $2,043. You just check my work process. Yep. $2,043.38. 0.377, so 0.38. Okay. These next two problems, your table will complete those after the video. Not right now. We're moving on to the next and final review topic of properties of exponents. This is a topic that always needs review every single time I teach anything involving exponents. Even in pre-calc, I'm reviewing these. So make sure you guys are focused here because you're going to see a lot of exponents. Okay, we've got a bunch of properties right here. So we'll go through these and then we'll do some examples together. So first of all, if you're multiplying two like bases, so base is the big number, exponents is the small number after the variable. So x to the a times x to the b, the property there, what do you do with those powers a and b? You can actually simplify that by just adding them together. So x to the a plus b. Let me show you a quick example of that. So if I have x squared times x cubed, I'm going to show you why we add them. This is x squared is just x times x, right? So x times x cubed, which is just times x 3 times. So I have x squared right here times x cubed. Really, I'm just multiplying x by itself 5 times, which is the same as 2 plus 3. So that's why if you have the same base, you add those exponents because it's just you're multiplying it by itself that many times and that many times. So for a total of x to the 5th time. So you're just adding those. Okay, the kind of opposite situation there is with x, the same base to a power divided by a same base to a different power. For those, you can actually just subtract the powers, a minus b. So it's whatever the exponent is in the numerator minus the one in the denominator. And then x to the negative. So when we simplify exponents, you should never have a negative. So if you do, you just want to rewrite it. And a base to a negative power is actually the same exact thing, just in the denominator of a fraction or reversed in the numerator. So if you've got x to the negative a, you can make it x to the positive a as long as you just put it in the denominator. Then we've got something raised to a power raised to another power. What do you do with those two exponents? You just multiply them together. So that would be x to the a times b. And then this one, you won't see this quite as much, but if you've got a whole fraction raised to a negative power, you can rewrite it to a positive power, positive c, as long as you just flip that, take the reciprocal b over a. And then there's a few other important things to remind you of. One is that anything raised to the 0th power is actually equal to 1, which is really helpful. And I can show you guys why that's true in class sometime. It's actually really cool to see why that's true and how we can reason that. We can reason through why that's true. Another important thing to keep in mind is if you have a variable raised to an exponent that is a fraction, like x to the 1 over a, that's actually the same as the root, the a root of x. So for example, if I said rewrite x to the 1/2, that's just the same as the square root of x. And we'll see that in a problem in one of these examples. Okay, so I'm going to do 3 examples with you. Properties of exponents are usually where I see a lot of mistakes, so make sure you guys are working through these with me, and then as a group, like talking through these, because there's so many details and it's easy to get mixed up here. Okay, so this one, number 1, I've got a whole bunch of stuff in the parentheses raised to the -1. So I'm going to use this property here. When I have something to a power raised to a power, you're going to raise everything in here to that power by multiplying. So what that means is I'm going to take -1 and it becomes the exponent of every single thing in here, including that 2. So it's going to be 2 to the -1 times x to the 4th to the -1. So I'm just multiplying 4 times -1. So that's x to the -4 times, just put a little times there, and then y to the -3 raised to the -1. So again, I'm multiplying -3 times -1. So it ends up being y to the +3. So this is just one step. Basically what I've done is, some people like to use the word distribute. I hesitate to use that word because we're not distributing. We're just raising everything to that -1 power. Distributing is more of a multiplication term. So I've got everything raised to the -1, but I'm not done simplifying because I have negative exponents. So we should never see negative exponents in your final answer. But I know that something raised to a negative power can be rewritten as a fraction with a positive power in the denominator. So that means instead of 2 to the -1, I could rewrite that as 1 over 2 to the +1, which is just 1 over 2. And instead of x to the -4, I can think of that as 1 over x to the +4. And then y cubed is already positive. I can still write it as a fraction, but y cubed just stays where it is in the numerator. Now I've got 3 fractions, and I can just simplify that to write it as a single fraction by multiplying all the numerators. So 1 times 1 times y cubed, which is y cubed, divided by 2 times x to the 4th times 1. So 2x to the 4th. And that's as simple as it gets. And the next one, right here, a lot going on here. Take it one step at a time. My first set of stuff, I have 3a and then squared. So I'm going to take the squared, everything on the inside of here is getting squared. So the 3 is getting squared, that's 9. A is getting squared, that's a squared. Then I have this whole piece being raised to the 1/2. Remember, something being raised to the 1/2 power is the same as the square root of that. So now what we can do is I can think of this whole thing, instead of that whole thing raised to the 1/2, I can think of the whole thing under a square root. And then I can simplify. So let's think about this. 25 is a perfect square. So I can take the square root of 25 and it's just going to get multiplied by whatever I have out here. A squared is also a perfect square because it's a squared. So when I take the square root of a squared, it's just a, and that gets multiplied out here. And then B, I don't know what B is, but it's probably, who knows, maybe it's perfect square, maybe it's not, but since it's a variable, we're just leaving it there. So I'm going to circle it because it's going to stay. Now I'm going to simplify. I have A times 5 times 9 times A squared. So 5 times 9 is 45. A times A squared is A cubed. And then I'm left with the square root of B on the inside. And then finally, I've got one more here with a fraction. You get closer. All right, 4 times x to the 0th times y to the negative 2 times z cubed, all divided by 4x. There's a lot going on here. Just take it one thing at a time. Let's start with the 4. 4 does not have an exponent. There's nothing to simplify here. However, there is a 4 in the denominator. So 4, we use the word cancel out. What happens is 4 divided by 4 is actually just 1. So that's why we're canceling out. So the 4 in the 4, that's just 1. So it's not going to change the value of this. Next I have, so if it helps and you want to write 1 in the numerator, that's totally fine. X to the 0th. Remember, anything raised to the 0th is 1. And if you want to see why that works out, remind me in class, I'll show you. So that's just 1 as well. So 1 times 1. Then I have y to the negative 2. Well, I want to write that with a positive exponent. So that means I'm going to move it to the denominator with a positive 2. And then next I have z cubed. Z cubed is just, it's totally fine where it is. Nothing I can really do with that. So times z cubed. So I have 1 times z cubed in the numerator. And then in the denominator, my y to the negative 2 got moved down here. And then I still have this x right here. So that's just going to be times x. And then we can just simplify. 1 times z cubed is z cubed. Y squared times x is just y squared times x. So your final answer has no negative exponents and only one variable of each. So there should only be one z, one y, and one x. So that's how that simplifies. And on the very next page, you see the problems that you guys will do as a group. So that ends a very quick review on these concepts, but you have all my examples. So I do expect you guys to work through these as a group. Go back to the beginning, work backwards. I don't care how you do it, but I do expect you to finish this in class with your team. You should have enough time. If for some reason you don't finish, please finish it for homework. If you do finish, turn it into the black tray, and then you can go. All right, y'all, that's it. See you soon.